Hello, welcome back to Chapter 10, Part 3. We are doing on standing waves today. So standing waves is a type of wave whereby the interference between two waves gives you an illusion of a standing wave or a stationary wave. So we have one wave going on the right, one wave going to the left, and when they superposition on top of each other, when they construct with each other, what happens is the outcome or the net of that two waves appears as if they are standing waves. What is standing waves? Standing waves is when you have only this part of the wave moving up and down. Kenapa dia hilang? Okay. This part moves up and down, but this part does not move. Okay? But when you look at it, it looks like this sebenarnya. When you just look at it like an instant, it looks like there's like two thingies, two eyes, right? So that's your standing wave. What happens is that there are two waves, they superposition on top of each other, they overlap, and the net of that overlap gives you the appearance of a standing wave, right? So let's talk more on this. So these are a few examples. So let's take a look at this guy first. Okay, so I have one wave going to the right, one wave going to the left. And when they overlap, let's say the top part, how do I say this one? How do I make this clear when it's moving? Okay, so when a maximum overlaps with a maximum, it gives you constructive interference, and then it oscillates up and down. And when a maximum overlaps with the minimum, the net of that wave becomes a zero, and it gives us this position. So this is a zero, whereas this guy fluctuates between maximum and minimum. Okay, so this occurs when constructive interference happens. Okay, constructive interference, and these points occur when we have destructive interference, which means that when they overlap, they cancel out with each other, gives you a zero. Destructive, It means that you are destroying that wave. Well, not technically, but destructive means like that. Okay, so you have constructive interference, which gives you the up and down, the maximum and the minimum, and you have destructive interference, which gives you the zero. Now these points have a name. The zero part is called a node. The node does not move. It remains at zero, or the baseline does not move. So that is your node. The part that keeps on moving is called the antinode. The part that keeps on moving is called the antinode. So remember, the part where you have these zeros, where it's not moving, is called a node. And the part where you have the maximum and the minimum is called the antinode. So that's the structure of a standing wave. So a node occurs when two traveling waves have the same magnitude of displacement. They have the same magnitude of displacement, but the displacement are in opposite direction. Like I said before, when you have a maximum and it and you overlap it with a different wave. Okay, so this is wave number 1, the red one, and wave number 2 overlaps with wave number 1 because they have the same magnitude, but they have the same magnitude or the same displacement, but they are in the opposite direction. So this gives you a zero. So the displacement are in opposite direction, the net displacement is 0 at that point. So 10, so this is a 10, this is a minus 10. So you get 0 displacement. X is equal to 0. The distance between the two nodes is half a wavelength. Nanti saya cakap lagi pasal ni. An antinode occurs where the standing wave vibrates at the maximum amplitude. So this is where the node happens, where you have two waves that overlap with each other. They have the same magnitude of displacement but in opposite direction. The antinode happens when you have a maximum 10 with a 10 and a minimum, -10 with a -10. So you get 20, and you get this, for this guy you get -20. So you fluctuate between the highest point to the lowest point, right? The maximum amplitude and the maximum negative amplitude. So that is called the antinode. Now, the distance between two nodes is half a wavelength. Now let's look back at the diagram just now. So we know that one wavelength looks like this. This is one wavelength. So if this is one node, this is one node, and this is one node, they said that the distance between two nodes is half a wavelength. So that is what it means lah. You have one wavelength, the distance between the two nodes is half a wavelength. So that's just something to know. You don't have to memorize. Just look at the diagram, understand it. Inshallah, tak payah. You don't have to memorize. Okay. Standing waves in a string. Just now I talked about the structure of a standing wave. What happens that makes a node? What happens that makes an antinode? Antinode, they fluctuate from maximum to minimum. Constructive interference. Node is when you have two maximum displacement but in opposite direction. When they overlap, the net displacement is 0. So dia jadi kosong je lah. Okay, so that's the structure of a standing wave. Now let's look at this example. It's a standing wave in a string. When a traveling wave reflects back on itself, you have a string, you vibrate it, right? You vibrate it forward. There will be a vibration going backwards as well. Reflection, right? We know that waves can be reflected. So the wave and its reflection interfere. Interfere ni maksudnya dia overlap. Interfere means overlap or superposition, according to the superposition principle. So they overlap with each other. Both of these waves overlap, and with exactly the right frequency, the wave will appear to stand still. You can try vibrating your string, and you find the right frequency, you'll see that it will give you a shape looking like this. Okay, so this is the wall. When you vibrate it at the right frequency, you see like it's almost standing still. But in reality, it's moving, but it looks like it's standing still. Okay, so nodes, here something to note off is nodes, the zero displacement must occur at the ends of the string, which means that it has to happen at the wall, at the end of the string. So that's just a fact for waves in a string. So mesti dekat end of the string, mesti wajib node tu mesti dekat end of the string. Dia tak boleh dekat antinode. It does not end at the antinode, it must end at the node, because these points are fixed. Okay, so this is something very important to take note of, because we will learn about standing waves in air. So it's a different situation. So untuk standing wave in strings, the nodes must be at the end of the string. Okay, so for the harmonic series, now you're asking me, Doctor, apa benda harmonic ni? Okay, hear me out first. So we have this equation, right? We have seen this equation from chapter 9, V equals to F lambda, right? So V equals to F lambda, and for a string, there is a new equation, V equals to tension over mu. Mu is mass over length. Mu is mass over length. T is tension in newtons. It's a type of force, right? This guy is in kilogram per meter. That's your SI unit. And the square root of these two units, these two parameters, gives you the speed of the string. Okay, speed of the wave in the string, sorry. Now rearranging this equation, rearranging V equals to F lambda, right? I want to solve for F. So F equals to, sorry, it's already there. So F equals to V over lambda. What I did was I just rearranged this guy. And I know that lambda is 1 over 2L. How do I know this? Okay, sabar. Okay. First of all, kita ada V equals to T, square root T over mu. So that is my V. Dah, settled. Lambda is given by 1 over 2L for the F1. Lambda is given as 1 over 2L for for F1. What is F1? F1 is the first harmonic of the harmonic series, or the fundamental frequency. Okay, you can use either one, but when they say fundamental frequency, it just means first harmonic. And as you can see from this diagram, the first harmonic is only, the length is only half a wavelength, because we know that one wavelength is this much. One wavelength looks like this. If it's only this part, then we know that it's only half a wavelength, right? So 1 over 2L, because half a wavelength, is your times with the T over mu, square root that, gives you the frequency. Okay? Alright. Kejap, kenapa saya padam itu? Okay. Okay, let me repeat myself about the lambda. So we know that lambda, sekejap, tengok gambar ni. Kita tahu lambda, our lambda or our wavelength should look like this, kan? And, which means that lambda is equal to, oi besar gila. Which means that lambda is equal to, okay, lambda is equal to 2L, twice the length of this string. If I want to substitute lambda into my equation, right? I want to substitute lambda into my equation, so it just becomes V over 2L. Betul tak? And I know that V is equal to T over mu, square root that. So substituting that, 1 over 2L T over mu. Sama tak? Sama. So this is the equation for fundamental frequency, or the first harmonic. Okay, so moving on to the second harmonic. So we have second harmonic, we have third harmonic. Just now, our first harmonic looked like this. It was half a wavelength. Now, the second harmonic is 1 full wavelength. The third harmonic is 3 over 2 wavelength, or 1.5 of a wavelength. Okay? So, in this case, L is wavelength. Look at L is wavelength. And in this case, L is 3 over 2 lambda. Okay, so back to our equation, we had F1 equals to 1 over 2L, right? This was for the fundamental frequency, T over mu, square root that. For the second harmonic, we have V lambda over 2, 2 over 2L, which just means 1, right? Because L is just lambda. Okay, so F equals to 1 over lambda, and this is T over mu, and I know that lambda is just L. Okay, okay, so let's continue. So this is F2, 1 over lambda T mu. This is which means that this is the this is V, and I want to substitute lambda for L. I want to substitute lambda in terms of L. So I know that for this guy, for second harmonic, this is 1 whole wavelength. So L equals to lambda. So I got that. So L equals to lambda, so it just becomes 1 over L, and times with T over mu. Okay, so that is your second harmonic punya equation. Now, let's do the third harmonic on this side. The third harmonic, draw. Hello, drawing. Okay, so F3. I want to know what is my lambda that I need to substitute. I know that my V is just this equation. So let's take a look. We decided that, okay, so we have seen this. This is 1 lambda and a half of a lambda. So it's 1.5 lambda. L is 1.5 lambda, or 3 over 2 lambda. So L equals to 3 over 2 lambda. I want to substitute lambda for L. So what should I do is I need to rearrange this equation to become lambda equals to 2 over 3L. So now I can substitute for lambda. F3 equals to 1 over 2 over 3 square root of T mu. And rewriting this will give me 3 over 2 T mu. Okay, so now let's compare these equations pula. So we have F1. Okay, let me rearrange everything so we can see the pattern here. So we have F1, 1 over 2L. Okay, oops, terlebih pula. Ini buat turun. Whoopsie. Right, that's good. And this guy, let's go here. Let's go. So this is my F1. I need to find my F2. My F2 is over here. No, it's this one. Right, this is my F2. Terambil semua pula. Kejap ah. Give me some minute. Give me some time. Ya, terambil pula divider. Okay, you stay here, please. Right. Okay, so F1, F2 tak cukup tempat. F2 over here. Okay, so F2 is that. So I have F1, 1 over 2L. F2, 1 over L. F3, 3 over 2L. Okay, so F1, 1 over 2L. So F1, 1 over 2L. F2, 1 over L. Salah lah. Okay, again. So I have F1, which is 1 over 2L. 1 over 2L. Okay, F2 is 1 over L. F3 is 3 over 2L. Now, can I rewrite this in a way that it connects F1 to F2 and it connects F3 to F1? I can. So this becomes 2 times F1, right? And I will get 2 times 1 over 2L gives me 1 over L, right? So this guy now becomes 3 times F1. So 3 times 1 over 2L gives me 3 over 2L. So rearranging this equation, now that I see the pattern, this is 1, F1, 2, F1, 3, F1. So it is a multiplication of the fundamental frequency. So this is how we get this equation. The next equation, the harmonic series or the harmonic frequencies. So Fn is given by n times the fundamental frequency, which is equal to n over 2L square root, this is your tension, right? This is also T over mu. Now, if you are looking for the fundamental frequency, this guy becomes 1, this guy becomes 1. So it's just F1. If you are looking for the second harmonic, so this is 2F1 equals to 2 over 2L square root T over mu, which just gives you 1 over L. Sama je macam kita buat tadi. So if you want to find the fourth harmonic, what you should do is you just substitute n for that number. So n should be 4. If you are finding the fourth harmonic, n should be 4 over here. So you get 4 over 2L times with tensions over mu, square root that. Okay, so this is the general equation and you can use it for your harmonic series. F1 is your fundamental, F2 is your second harmonic, F3 is your third harmonic, F4 is your fourth harmonic, and so on. Okay? Okay, so let's take a look at the structure of our waves. So this is our F1, right? F1 has 2 nodes. So N node, N is your node, N is node, and A is antinode. So dia nak tunjuk structure je kat sini. So fundamental frequency has 1 antinode and 2 nodes. And then this guy, 3 nodes and 2 antinodes. So 1, 2, 3, 1, 2. Node, antinode, node, antinode, node, antinode, node. So you get that. Okay, so just take a look at the structure, try to understand what is node, what is antinode, how does the fundamental frequency look like, how does the second harmonic look like, how does the third harmonic look like. Okay, it's very important for you to visualize. So if they ask you, okay, draw the fourth harmonic frequency, fourth harmonic wave, so you have to know how it looks like. Okay, so standing waves in a string, you have this equation. This is your conclusion. Very important equation. N is the number of your series, number of harmonic series. So if they ask you what is the fundamental frequency, N equals to 1. Second harmonic, N equals to 2. Okay, and so on. L is the length of the string, T is the tension in the string, and mu is the mass per length of the string. That is the characteristic of the string. So it depends on the string. It depends on the mass and the mass per length. Okay, moving on. So let's do this example. A string that is 50 centimeter long, so length is 0.5 meter, has a mass per unit length equal to 20 times 10 to the minus 5 kilogram per meter. Do I need to convert this? No, this is already in SI. To what tension? So it's asking, what is T? To what tension should this string be stretched if its fundamental frequency is to be 20 Hz? So dia cakap, what is T if F1 is equal to 20 Hz? What is T if F1 is equal to 4,500 Hz? Okay, so this is very straightforward. It's just you using the equation that we have learned. So Fn equals to Fn F1 or equal to N over 2L square root T over mu. Okay, saya pun baru belajar juga tadi sebab saya pun tak ingat equation. Okay, so that let's just plug it in the number. If our F1 is 20, so let's use this 1, N is 1, right? Because it's a fundamental frequency. 20 equals to 1 over 2L. We know what L is, so let's just substitute terus. 0.5. Okay, and I am looking for T. Mu is 20 times 10 to the minus 5. Okay, so solving for T, I get 4050. What is the unit for tension? It is a type of force, so your unit is newtons. So that's your first example. For A, what if the fundamental frequency is 4,500? Okay, so 4,500 sama juga 1 over 2L. We know what L is. The length is not changing, so it should be straightforward. So T over 20 times 10 to the minus 5. Sama juga, solve for T. So you get, silap, ini bukan, ini 0.08 Newton. This guy is 405 Newton. Okay, so that's a that was an error from my part. Okay, so that is example 10.5. The tension should be 0.08 if the fundamental frequency is 20 Hz. So this is your A, this is your B. And the tension should be 4050 Newton if your fundamental frequency is 4,500. Alright, moving on to the next example. A stretched string is 160 meter long. Convert this to SI unit. Let me use blue so that we have a distinction between the two. So this is 1.6 meter. Okay, and it has a linear density of 0.015 kilogram per centimeter. This is not in SI unit, so I have to convert that. So this becomes, okay, you already know how to convert this. I'm just going to give you the answer, times 10 to the 3 kilogram per meter. So that's in the SI unit. So again, what tension in the string will result in the second harmonic? So now it's asking for the second harmonic of 460. Okay, so the frequency is 460 and it is equal to NF1 it is also equal to 2 over 2L. Your L is 1.6. And then you are finding your T. Your mu is 1.5 times 10 to the 3. Then you solve for your T, right? So 460 times 1.6, you square that, times it with 1.5 times 10 to the minus 3. So you get your T as, if I'm right, 81254 newtons. So that is your answer. I'll see you in the next part. Bye-bye.